In this video, I'll discuss our recent publication, Diffusioosmosis-driven dispersion of colloids, a tailored dispersion analysis with experimental validation, with a focus on the microfluidic experimental aspect. The work is published in the Journal of Fluid Mechanics in May 2022. The main storyline of the work is about obtaining an appropriate one-dimensional equation that can describe the distribution of a particle patch undergoing diffusiophoric translation and diffusiosmotic dispersion. We focus on the diffusiosmotically induced liquid flow in dead-end pores under a salt gradient and apply tailored dispersion idea to include the effect of flow-driven dispersion in the effective diffusivity of a particle patch. By going through 1, 2, and 3-dimensional features of the experimental system, we motivate the need for the current theoretical approach and the experimental validation. Now let's look into the details. Diffusiophoresis is the spontaneous motion of colloidal particles under a solute concentration gradient. If a spherical particle with a negative surface potential is located under a concentration gradient of salt, there is liquid flow generated along the surface, which is called diffusiosmosis. Such a surface flow will shear the particle in the opposite direction at speed up, and the resulting motion is diffusiophoresis. The simplest form of the diffusiophoric velocity formula for a system with a symmetric electrolyte is mobility times grad log C. Here, gamma p is the diffusiophoric mobility for ZZ electrolyte, and C is the concentration of salt. For more detailed explanation of diffusiophoresis, please refer to the inserted video in the top right corner. Scientists have actively demonstrated diffusiophoric migration of micron-sized particles, as the typical diffusiophoric mobility induced by a common salt gradient like sodium chloride is 1,000 times higher than the particle's Stokes-Einstein diffusivity. Since 2008, Microfluidics has become an extremely popular platform for studying diffusiophoresis of micron-sized particles. By using various channel designs, scientists were able to create steady-state or transient concentration gradient of solutes. These system designs and more detailed features of microfluidic diffusiophoresis experiments are thoroughly discussed in my recent review article. So I'll start talking about one channel design that we frequently used in our research, which is the dead-end pore configuration. The dead-end pore geometry has this typical design. Narrow pores are located at one side wall of the main channel, so that both the transient solute gradient and the corresponding particle motion can be observed along the pores. Such a configuration is known to be useful for studying one-dimensional diffusiophoresis, as the salt concentration profile is nearly one-dimensional inside the pore. In this way, we can compare the experimental results with one-dimensional solute diffusion equation and the particle advection diffusion equation. In the experiments, depending on the choice of the initial and boundary conditions, we can entrain particles into the pore along the solute gradient, compact existing particles toward dead end, or withdraw existing particles by changing the sign of the solute gradient. Here we're seeing the typical experimental videos obtained from the entrainment and compaction configurations. In these systems, negatively charged polystyrene particles in the main channel move into an initially empty pore, or the same particles that are initially located in the pore move toward the dead end by diffusiophoresis. To compare with one-dimensional transport equations, we detected the fluorescent intensity distribution at different times, and the peak location was chosen as the comparison parameter. As you can see from the comparison plots, this strategy works well, and we were able to investigate diffusiophoresis of polystyrene particles under multivalent electrolyte gradients and in the presence of varying zeta potential. So far, it appears that the dead-end pore experiments are meeting our needs by confirming the predictions of the one-dimensional model. However, the actual experimental setup is three-dimensional, and we're capturing the two-dimensional picture, which is the height-averaged view of the dead-end pore. So if we revisit the compaction experiment with a focus of individual particle level behavior, we see that although the collective behavior of particles appears almost one-dimensional, the two-dimensional effect emerges as a curved particle boundary. Such a shape tells us that the particle velocity is not uniform across the pore and suggests that there may be cases where the one-dimensional diffusiophoresis model is not enough for predicting the particle behavior. Then what is actually happening inside the pore in the presence of a one-dimensional solute gradient? The solute gradient that moves particles also generates the diffusiosmotic flow along the pore walls. In microfluidic experiments, PDMS is commonly used as the channel material, and its surface typically exhibits a negative surface potential when in contact with an aqueous phase. Therefore, the direction of wall diffusiosmosis is in the opposite direction of the polystyrene particle motion. This surface flow sets up a non-zero pressure gradient in the pore and induces bulk flow that has a parabolic velocity profile. Therefore, the effective velocity of particles is not anymore just the diffusiophoretic velocity, but the sum of diffusiophoretic velocity and the local flow velocity. As a result, the compaction boundary is not flat but instead takes on a parabolic shape. By including the two-dimensional flow effect and considering the multi-ion diffusiophoresis, we were able to predict the profile of the compaction system, which agrees well with the experimental data. Now that we have confirmed the influence of the two-dimensional flow effect as a parabolic compaction boundary, we proceed to test another configuration where an additional dimension must be included in the analysis. Now let's consider a configuration where a patch of particles is introduced at the inlet of the pore and translates along a salt gradient. To set up the salt gradient, we used 1 and 10 millimolar sodium chloride in the main channel and in the pores. We observed that when using 3 different pores with the same width and length but different heights, the particle behavior varied. In the inserted clips, you can see that the initial particle patches look almost the same in the 3 pores, but the translation and dispersion behaviors are clearly different. So at this point, an important question arises. What is a good one-dimensional representation of diffusiophoresis in a 3-dimensional dead-end pore geometry? Unlike the entrainment and compaction configurations, detecting the peak location in the intensity plots was not effective in characterizing the behavior of the particle patch. Also, the two-dimensional parabolic flow velocity cannot explain the difference among these pores because the 2D flow velocity is identical in these 3 two-dimensional videos. We created these schematics to illustrate the different layers in the pore and how the particles are distributed at different heights under the same salt gradient. In the compaction configuration, the parabolic boundary at different heights are averaged out in 2D imaging, so that the apparent boundary observed from the experiments can be nicely described by the two-dimensional simulations. However, in the particle patch configuration, the particle dispersion pattern in different Z layers is not averaged out in the imaging, but reveals the full 3D flow structure inside the pore. So obviously, the two-dimensional flow velocity cannot explain the different widening behaviors of the particle patch in the pores of different heights. So now we consider the 3-dimensional flow effect. As you can see from the plot, the height averaged velocity, which is the orange curve, is similar to the two-dimensional parabolic flow velocity, which is the green curve. Therefore, in the compaction experiments, it was okay to use the 2D velocity to predict the compaction boundaries. For the particle patch system, comparing the experimental images with the velocity plots near the wall and at the center line qualitatively confirms the 3-dimensional flow effect. If you pair the solid and dotted lines with the same color and focus on the difference of the 2 velocities, you can see that it qualitatively tells you the width information of the particle patch. The trend of the patch size agrees well with the flow velocity distribution in different pores. From this analysis, we can conclude that it is primarily the diffusiophoretic velocity that translates the particle patch, and it is the diffusiosmotically induced liquid flow that disperses the patch to the widths corresponding to the local flow velocity. We noted that such a configuration is similar to the flow-driven dispersion problem in a pipe flow. The only difference is that in the pipe flow, the patch translates and disperses by the imposed flow velocity, whereas in our system, the patch translates at the diffusiophoretic velocity and disperses by the flow velocity. Using the analogy between our dead-end pore and the pipe flow systems, we were able to apply the Taylor dispersion idea with the listed assumptions, and we were able to reduce the three-dimensional transport equation to a one-dimensional equation. This is done by taking the area average of the equations and considering the symmetry of the three-dimensional flow structure. As a result, we obtain the effective diffusivity of the particle patch that includes both the particle's own diffusivity and the influence of the three-dimensional flow velocity, which is of course closely related to the wall diffusiosmotic velocity. To validate our Taylor dispersion analogy, we designed a new set of experiments with a long pore. To remain within the regime where the Taylor dispersion concept applies, we selected a pore length large enough such that the typical timescale for a particle to translate to the pore end is much greater than the typical timescale for it to diffuse across the pore. For 0.5 micron carboxylate modified polystyrene particles in a sodium chloride gradient, we were able to predict the diffusiophoritic translation and diffusiosmotic dispersion pretty well. Only by including the three-dimensional flow velocity can a correct particle distribution be obtained in the one-dimensional diffusiophoresis experiments in a three-dimensional pore. We also confirmed that our one-dimensional model with effective diffusivities predicts well the behavior of particles of different sizes or different diffusivities. Finally, we directly compare the 1, 2, and 3-dimensional models without any dispersion with 2 and 3-dimensional dispersions. For the systems where three-dimensional effects are not averaged out along 1 or 2 dimensions, full consideration of the three-dimensional flow effect is necessary because we are never free of the diffusiosmotically induced liquid flow in the experimental systems designed for diffusiophoresis. To conclude, we investigated a dead-end pore system where three-dimensional flow effects are not negligible in the analysis of particle diffusiophoresis. To unravel the three-dimensional information in one-dimensional diffusiophoresis experiments, we focused on the analogy between our system and the Taylor dispersion configuration. By applying the Taylor dispersion idea, we were able to reduce the 3D transport equation to the one-dimensional equation with an effective diffusivity, and it was further compared with long pore experiments. We suggest that knowing 3D flow structure is important for identifying correct particle distributions in dead-end pore experiments of diffusiophoresis and also in other geometries. Please read our published article for more details of the model derivation and the experiments. Thank you for watching this video, and please feel free to reach out to me or any of the co-authors if you have any questions about this work.